Thank you, Ellen. I have to update my bio because I think I just passed 4 decades. So that just means I'm old. That's all it means. So thank you, everyone. Again, any questions you have, please write them down, and we'll, if we don't get to them at the end of this webinar, we will email you with the answer at a future date. So we're going to discuss mitigating shock hazard with the absence of voltage tester and UL 943 shock protection panels. So in the electrical hazards, we have electric shock. An electric shock is an injury caused by electric current passing through the body. We have arc flash. Everyone's aware of arc flash. I think the industry has done a tremendous job bringing awareness to arc flash and arc blast, such that the number of incidences have decreased greatly for arc flash and arc flash. I wish I could say the same for our electric shock, because the industry has not really kept up with shock hazards. So the arc flash is a sudden release of energy caused by electric arc resulting in intense heat, and an arc blast is a pressure wave caused by a rapid expansion of air and metal during the electric arc blast. So you basically have molten copper and molten steel basically coming right at you because it's in an enclosure. So there's a danger in that. So we can see here that EFSI has kept a track record of electrical fatalities and electrical injuries due to electricity. So no significant decrease in electrical in fatalities and challenges remain in reducing from the electrical incidences. So although and this goes back to what I said earlier, we've done a tremendous job bringing awareness to arc flash, that we don't follow suit with arc electrical fatalities and electrical injuries due to shock. There are still a tremendous amount of people getting hurt due to contact with electrical equipment, working on or near electrical equipment. You could see in 2020 was the lowest, but we could say that was due to COVID because not many people were working. But we've had some sharp increases since then. You can see 126 fatalities in 2020, 152 in 2021, and in 2022, 195. And injuries have increased at the same rate. So you can see that we're not really becoming more aware of our surroundings, and we're having many issues near electrical equipment. So what's the cost for this? Well, the ESFI has done a study, and they found that 32% of electrical injuries have been caused by electricians or people with more than 5 years of experience of working on the electrical equipment. 33% from 1 to 5 years. So this sort of disqualifies the myth that this only happens to junior electricians, trainees, apprentices, because 65% of electrical injuries are caused by people with more than 1 year of experience. So approximately 48% of reported fatalities occur while working on or near energized equipment. So this could be working on equipment where you think is non-energized but is energized, or becomes energized when you're working on it. So we're going to discuss the absence of voltage testers, see how this will help the industry in electrical shock hazards. So there's three main electrical standards for working on or near electrical equipment. NFPA 70E is updated every 3 years, CSA Z462, and OSHA 1910.333. So you can see that NFPA 70E is a standard for electrical safety in the workplace, a state in which electrical conductor or circuit part has been disconnected and from energized parts, locked out, tagged out in accordance with the electrical established standard, tested to verify the absence of voltage. CSA basically has the same verbiage, but it's important to say that it's tested to ensure the absence of voltage. OSHA, you can lock something out, but you have to verify and test to ensure that there is an absence of voltage. So I've traveled all over the world, and I've done this speech all over the world, and it's very, I think United States and Canada are probably the only domains that actually define how to verify the absence of voltage. So from 2015 to 2024, the code cycle has changed 4 times. So you can see that in 2015, verification of an electrical safe work condition is the use of an adequately rated portable test instrument. You're looking at a voltmeter. To test each phase conductor or circuit part to verify de-energize. Test each phase conductor or circuit part, both phase to phase and phase to ground, before and after each test. Determine that the test instrument is operating satisfactory through verification to a known source. So you take your voltmeter, you test phase to phase, you test phase to ground, you test to a known source before you do all that, and you test to a known source after you've done all that. And that was satisfactory in 2015. But as the records show, in 2015, 16, 17, we really didn't improve electrical safety. So in 2018, we modified, or the NFPA 70E was modified to include an adequately rated, permanently mounted test device shall be permitted to use to verify the absence of voltage. This caused a lot of confusion in the industry because there were products that were permanently mounted test devices, but were not suitable for use as absence of voltage testers. So these were operating lights. If the light's off, the voltage is off. If the light's on, the voltage is on. This was not an adequately rated test instrument. So in 2021, it came back with a permanently mounted absence of voltage tester shall be permitted to be used. So this tried to basically say that, we can't tell you what product to use, but it has to be an absence of voltage tester. So a permanently mounted absence of voltage tester can be used to verify the absence of voltage as long as it did everything that was associated with 120.5 Clause 7. And in 2024, a new part was added and have a test done at each point of work. This disqualified, or not disqualified, but made impractical the use of high impedance devices because they are not absence of voltage testers. So when you test for the absence of voltage, you have to de-energize the electrical equipment. You apply the locks, and as per lockout tagout instructions, select and inspect and put on your PPE, open the panel, test the tester to a known voltage source, test for voltage, and retest the tester on a known source. Studies have shown that 18.3% of facilities experience personal injury while using handheld voltage test instruments. 36.7% reported near misses of personal injury, and 11.7% of facilities with interruption to plan operations due to voltage testing incidences. So even though people are following the procedure prescribed, there's still human error involved in doing the traditional approach. So it took about 20 minutes to open the panel, test the tester for known voltages, test for a voltage source, and retest the tester. So this takes time as well. So time is an asset that we really don't want to play with, but we do want to take the time to make sure that the voltage is not present on the system. Sorry. So challenges with the traditional approach. Exposure to electrical hazard. You have to treat the equipment like it is live, and the hazard is there until you can verify the hazard is not there. So there's a risk involved in assuming you're safe. What bothers me the most is having a false sense of security. When you open up the panel, you can't assume the voltage is off and there is no hazard. There is always going to be a hazard. You have to understand your electrical equipment. How many sources do you have coming in? When I make a UL or a CSA panel, if there's more than one source coming to that panel, I have to put a sign that says this panel is fed by multiple sources. That must be adhered to. So the user has to understand that we disconnected one source, we have to check to see if there's any other sources, or ensure that we shut off that other source first. So you have to understand where the limitations are. So handheld testers expose workers to electrical hazard, having on the wrong setting, using the wrong instrument. Proximity sensors cannot be used to test for the absence of voltage because their limit is 80, 90 volts, depending on which one you have. And they do not measure DC voltages. So there's a risk involved in using the wrong equipment. They're great for determining whether you're in the right circuit or not, for troubleshooting, but they're not an absence of voltage tester. Risk of human error. I mean, I built and designed neutral grounding resistors. My test instrument, 90% of the time is on resistance because I'm measuring ohms. When I have to test voltage, I got to make myself conscious that I have to change the setting to volts and measure volts. And AC or DC. Lack of compliance with safety standards. Many workers neglect lockout tagout procedures and expose themselves to live equipment risk. Consisting violations of lockout tagout standards is a top of OSHA violations. This comes down to training, and there are multiple companies that you can get training from to adequately satisfy and train personnel for the proper usage of equipment and how to safely work on electrical equipment. Sorry. So back to 2015. Well, 2018, we added an exception of Rule 7, permitting the utilization of a voltage test port for performing the absence of voltage tester. Well, putting in a test port means basically you can test the voltage on the test port. However, when you measure the absence of voltage, all you've really verified is there's no voltage present on the test port. Again, you don't want that false sense of security to translate to that there's no voltage present on the bus. You verify the absence of voltage on the test portal, not on the bus. And this is why in 2024, it went to at each point of work. So they're trying to say, you're not working on the test portal, you're working on the bus, or you're working on something below the bus. So that's what you want to verify. In 2021, to try to alleviate the problem, it went to a permanently mounted absence of voltage tester. Now, there's specific rules associated with the absence of voltage tester that does not apply to the permanently mounted test device. A permanently mounted test device could be a light. You can call a light bulb a test device. It's not an absence of voltage tester. So, sorry. So voltage indicators for verification of absence, the challenges involved with that. Voltage indicators show only the presence of voltage, but cannot confirm the absence of voltage. How do you confirm you'll have no voltage present on the bus? Your voltmeter reads 0. This is why you have to verify your voltmeter is working on a known source, so you have deflection. False 0 readings. The test port does not guarantee no voltage on current carrying conductors issue like missing a loose wire or a blown fuse. If there's a fuse, all you've done is verify that the fuse is blown. You don't want to have that false sense of security that says the bus is de-energized if your fuse is blown. There's lack of trust in the results. I mean, it's your life. You have to value the tools you're using to ensure that you are going to be safe in the workplace. Qualified workers may not fully trust instruments from test portals and may open electrical equipment from physical inspection, increasing the risk of unintentional contact. So there's lack of trust in the results. Risk of voltage exposure. Voltage indicators can bring voltage to the door, exposing risk due to potential voltage present. When I was building switchgear, I was told specifically, we learned that you can't bring more than 150 volts to the door. Yet we're bringing 480 and 600 volts to the door sometimes with some of these test portals. And that's not done. And it depends on which standard you're using. I understand there's different standards. In some panels, you may be able to do that. Switchgear, you're not be able to do that. So 2021, we're going to go to an absence of voltage tester. So we've tried to demystify the conflict, because permanently mounted test device is too vague. And when people have vagueness, there is no clear-cut choice of what to use. So NFPA 70E and Z462 came out and said that you need to use a rated permanently mounted absence, and a permanently mounted rated voltage absence of voltage tester is just that. It's an absence of voltage tester. It only gives you a positive signal when there is an absence of voltage. It's used to verify the voltage in electrical circuits or equipment is de-energized and free from hazard voltage before maintenance or repairs, reducing the risk of electrical accidents. It gives you a positive indication that there is a presence of voltage because you have 3 red lights. So you have 3 red lights when the voltage is present. It gives you an indication of absence of voltage. So when you shut your circuit off, you get 0 indication of anything is happening. You have to press the test button. When the test button goes out and does its test, and we're going to see what the test is fairly soon, it's going to come back, and if the voltage is between 3 and 600 volts, it's not going to be green. If the voltage is less than 3 volts AC and DC, then you're going to get 3 green indicators telling you that the voltage is truly absent. So the IAVT, is what we call the absence of voltage, is safer and quicker approach. You de-energize electrical equipment, apply the lockout tagouts, press the test button, wait 10 seconds. If you get 3 red lights when the voltage is present, you get a flashing amber light, 2 amber lights when it is unsafe or the voltage is not less than 3 volts, or if there's something else wrong with the circuitry. Only if there's nothing wrong with the circuitry, we are connected properly, do you get 3 green lights indicating there's truly no voltage present on the bus. So unsafe, unsafe, safe. So basically what happens is the absence of voltage tester is going to check the supervisory circuit to make sure the voltage is off. Supervisory circuit verifies the sensor leads are connected. Supervisory circuit verifies that the energy level of the bus is low enough to conduct the test. Supervisory circuit verifies that the voltage source is sufficient to conduct the test. Test the voltage that AC is less than 3 volts. Conduct connectivity check to ensure that the cables are connected correctly. Test and verify the DC voltage is less than 3 volts. Conduct connectivity check to ensure that all cables are connected correctly. Test the voltage again to make sure it's less than 3 volts, AC and DC. Test the circuit again. Supervisory circuit indicates that the tester functionality is satisfactory to complete the test. Okay, now we're down to a decision. We're all green. We've passed all these tests. We have 3 green lights. You don't pass one of these tests, you're not going to get 3 green lights. And this all took longer for me to read it, 10 seconds. No, less time for me to read it than 10 seconds. So in comparison between the test, the traditional with a voltmeter, we have no exposure where before we had 18.3% exposure or near misses in the verification process of testing for the absence of voltage. Now we took 10 seconds and you have a better sense of security entering that piece of equipment. And basically how it's connected is you have a door-mounted indicator connected with a communication cable or a we had a Cat5, now we have an IX connection between here, the display unit, and the control unit. A pair of wires connected to A phase, B phase, C phase, and ground. And why we have a pair of wires is we have to verify the continuity of the circuit to the bus. And we have to measure the voltage. So we're measuring the voltage phase to phase, phase to ground. We're also verifying that it is connected to A phase, B phase, and C phase. The only way I can think of to verify the connection is having a pair of wires go to each one. So the benefits of an absence of voltage tester. Part of UL 1436 is another standard that you have to pass. It's the functional safety IEC 61508 and SIL3 certification. You have to ensure that the equipment is going to be reliable for a long time. This comes down to component selection, methodology of firmware, and other important factors that can deteriorate your equipment faster. So we have to ensure that we have less than the failure rate has to be less than 1 in 10 million hours of operations. So SIL3 is a very, very stringent standard. And this is the biggest obstacle we had in getting this unit approved. So you have to test the hardware. It's a horrendous thing. And I don't want to get into it anymore because it was a pain getting through the first time. So what do other standards specify? Compliance with CSA Z462 and NFPA 70E. Use an adequately rated portable test instrument to test each phase conductor or circuit part and verify the absence of voltage. So on electrical systems above 1,000 volts, non-contact capacitive test instruments may be used. This is only for above 1,000 volts. But below 1,000 volts, an adequately rated, permanently mounted absence of voltage tester may be used to test for the absence of voltage of the conductors or circuit part of the work located, provided it meets the following requirements. So the requirements are more or less the same between Z462.24 and Article 120.6 of NFPA 70E 24. The IVT is a permanently mounted and permanently installed following the manufacturer instructions that conducts tests on the conductors at the point of work. It is listed and labeled for the purpose of testing for the absence of voltage. It tests each phase conductor or circuit part, both phase to phase and phase to ground. The test device is checked to make sure that it works well with a known voltage source, both before and after the test voltage. So the absence of voltage tester is very much specified in CSA Z462 and NFPA 70E. Now, 1436, the product standard itself. The product standard says that a permanently mounted test device that is used to verify the circuit is de-energized prior to opening an electrical enclosure, contains energized electrical equipment or circuit parts. An absence of voltage tester shall be provided with means for the user to initiate the test. So there's a test button involved. The absence of voltage tester shall provide user with a visual indication and confirm the absence of voltage after the absence of voltage test has performed the test. So this is the 3 green lights. The absence of voltage supervisory circuit incorporates a secondary power source and shall have no internal failures that would affect performance. So there's 2 particular manufacturers that have absence of voltage testers right now. One of them uses a battery, one of them uses we use a supercapacitor, so it's always self-charging while the circuit is on. The absence of voltage testers incorporate a test circuit to verify that the tester is functionally proper. So every time you test the absence of voltage tester, the first thing it does is test itself to make sure that it's functional, because you don't want a false sense of security. The absence of voltage tester visual indicators shall not illuminate green unless all 3 phases and leads have contact with the source. This is why we use a pair of wires going to each phase, because we have to verify the instrument by the standard has to verify connectivity to the bus. The AVT indicator shall not illuminate green unless the phase conductors and ground leads are connected according to the phase conductors. The visual indicator shall not illuminate green unless the secondary power source is operational. That almost goes without saying. I missed this one. The AVT indicator shall not only eliminate green when the phase-to-phase or phase-to-ground voltage measure less than 3 volts AC or 3 volts DC. When you're measuring voltage the traditional way, I'm not sure at what voltage level you can safely assume that there's 0 volts, because some circuits have decaying capacitive voltages. So somebody has to make the determination when you're doing this a traditional way, what is the low limit that you want to test and say, I no longer have voltages. If you're using test lights, they're going, especially LEDs, they're going to drop off around 20 to 60 volts, depending on the circuitry. Proximity sensors, they don't go below 95 or 80 volts, and they definitely don't do DC. So the AVT shall comply with the standard for functional safety IEC 61508 and achieve SIL 3. SIL 3 is not the highest level that is defined in 61508, but it's the highest level assigned for this particular standard UL 1436. You can go to SIL 4 and UL 1436 decided that SIL 4 was probably not necessary for this. So, voltage presence and indicator. The VTI, voltage test indicator, integrates the feature of a voltage indicator displaying the presence of voltage in each phase and each ground of the high impedance protected device. This is not to be confused with an absence of voltage tester. This is a troubleshooting tool. So you get voltage indication for the green lights or flashing red lights from 20 to 1,000 volts DC, AC DC, and test points from 0 to 1,000 volts. No power supply needed. You can measure under voltage, phase rotation, phase failure, harmonic analysis, phase rotation. Touch safe points. So you can't put your fingers in there. Voltage present through redundant LEDs. So this is a test portal and a test portal and test voltage indicator. So we got 2 LEDs per phase and a test probe. So in NFPA 70E Annex 0.2.4, additional safety by design methods. You can use these high impedance devices to reduce shock, because now you're measuring the voltage outside the gear. You don't have to open the door and measure the voltage inside the gear. It's great when the voltage is present. It's not a good indicator when the voltage is not present. Well, I missed that part. So you can see here, the following method have proven to be effective in reducing electrical risk associated with the arc flash and electric shock hazard. So what we've done is we've combined the two into one. So obviously with the absence of voltage tester, you can't measure the voltage on the bus, but you can with the test portal. And you can't measure the absence of voltage with the test portal when you have the absence of voltage tester. So we've combined the two into one unit. So you have UL 61010 indicating the presence of voltage. You can use the test portal to comply with 70B. You have a known voltage source and the absence of voltage tester tested UL 1436. So this gives you the absence of voltage tester for measuring the absence of voltage and the test portal for measuring the voltages on the bus. And this one is only, the test portal is only listed to UL 61010, while the absence of voltage tester is verified and tested to UL 1436. So which one do you choose? If you want a visual indication that the voltage is present, then use lights. You can use lights, that's not a problem. But know the limitations of what you're choosing. Voltage indicator with test portal, you can use the VTI. That gives you the lights indication and you can measure the voltage on the front of the bus. If you want to measure the absence of voltage, you get the presence of the voltage on the bus. You can't measure the voltage on the bus with the absence of voltage tester. The visual indicator on the absence of voltage, yes, you get a positive indication that you have the absence of voltage, and it has a built-in power, secondary power supply. It's listed to UL 1436 with SIL 3 according to UL or IEC 61508, and it meets the requirement to verify the absence of voltage in NFPA 70E 2024 120.67 exception 1. Or if you use the combination, you get everything combined. So you can combine the absence of voltage tester with the voltage test indicator and a built-in test port. So now we're going to get into special purpose voltage circuit interrupters. So there's a new, well, not a new standard, but a standard came out, the Outline of Investigations for Special Purpose Ground Fault Circuit Interrupters, UL 943C. We all know what UL 943 is. It's a GFCI Class A. Well, there's UL 943 Class Cs, GFCI Class C, Class D, and Class E. So we're going to get into that a little bit. And basically the purpose is the standard IEC 60479-1 indicates that you have how much current and how much time their body can handle the current before you have ventricular fibrillation. And we want to prevent that from happening. This is why we started with the GFCI Class A's in the first place. We wanted to make sure that where you're at risk of having water and electricity mixed together, you have to put in a GFCI Class A. Well, for industry, a GFCI Class A wasn't really good enough because when you have greater than 5 or 6 milliamp, you may have a three-phase device that is has more leakage current, or the unbalance of the currents is going to be more than 6 milliamps. So GFCI Class C comes down to 20 milliamps. Class C, Class D, and Class E is 20 milliamps. Still faster than the Dalziel and Beagle-Meyer curves, and it's faster than the curves in 60247. I forget the name right now. So how you determine what you need is you look at your system voltage. If the voltage to ground is greater than 150 volts, you have to go with the ground fault circuit above 300 volts. Okay, determine if it's over 300 volts or less than 300 volts. So if you have a 480 volt system, your voltage to ground is less than 300 volts. So you have to use a Class C 20 milliamp rating. If it's greater than 300 volts to ground, say for example, you have a 600 volt system, 347 volt, 20 milliamps with restricted requirements of low impedance grounding path. And Class E is a super fast isolating device. So 150 volts to ground or less, you use a 5 milliamp rating. Greater than 150 volts, Class C, D, or E, you can use those. And we're coming up with these products to do all this. So basically the curve is T is equal to 20 divided by I raised to the power 1.43, and you end up with this curve. Class A, Class C, and Class A is 943 in the US, harmonized with 144.1, and I believe there's a Mexican standard as well for that. Class C right now is only 943C, and EGFPD is UL 1053 or CSA 144. Basically, the system is working like this. You have a fault, you have any kind of leakage current, 20 milliamps or more. We monitor the current on all three phases, and we trip the circuit breaker if that current increases above 20 milliamps. And this is basically what the panel is going to look like. Class A, we have 6 milliamps at 208 volts at 40 and 100 amp let through current. Class C, 20 milliamps, 208 to 480 volts, 100 amp, 40 amp. Class D, 20 milliamp trip circuit, 600 volt, 40, 100, and 225 amp circuits. And EGFPD, 6 milliamp, 480, 600. You know that these ones, I can't call Class A because they're over 150 volts. So they're 100 amp and 100 to 300 milliamp let through current, trip levels, adjustable for 480 and 120 volts. One of the last things I want to touch upon is 421, M421, use of electricity in mines and I think OSHA has another clause where you have to monitor the frame voltage when you have a ground fault. So the frame voltage, the frame voltage is basically M42123 clause 4.6.5.1 requires ground circuit systems for movable or mobile electrical equipment to limit transfer potential below 100 volts for a duration of 1 second or less. Also, NEC Article 250, 250.188, systems supplying greater than 1,000 volts must have high impedance neutrals. Metal parts and equipment must be grounded to prevent buildup of, and ground fault current should not create more than 100 volts between the frame and ground. So we have a device that does just that. This is our GCHK. It was initially produced for the mining circuit in Canada because we've had this in our code for a long, long time. So we can monitor the frame voltage of 40, 60, 80, and 100 volts up to, well, minimum 4 kV right now. And we have this device that's available, and it monitors ground fault protection, ground check continuity, and monitors the frame voltage and a ground fault relay. Sorry I took so long. Are there any questions?
Thank you, Sergio. That was great. Yes, we have a bunch of questions, so I'll jump right into those. And as we said earlier, if we don't have time to get to all of these, we'll definitely be getting back to you via email. You still have time to submit the question, so if you do have one, please type it into your question window on the side of your screen and hit the submit button. So let's see. Let's start with someone's asking, will voltage be present on the door when the absence of voltage tester is installed?
No, we have no. It's a low voltage signal that we send to the absence of voltage tester from the control unit. So there's less than 3 volts on that line going to the display unit of the absence of voltage tester.
Okay, great. This looks like a general one. Someone's asking, is there any data showing the difference in injuries from electricians with only field training and electricians who attended an apprenticeship program or some other proper education and training?
There might be, but I don't have that information. That's a good question. I'd like to know the answer to that one myself because, first of all, I didn't think you could get an electrician license without going through an apprenticeship program, but I could be wrong.
Right. This is related also. So if awareness, training, and experience have not resulted in a reduced trend in fatalities, they're asking, is it your opinion, in your opinion, what other additional methods or strategies should be considered?
I don't know. Well, whatever we've been doing up till now hasn't been working. So we need a paradigm shift to make things better. In the UK, for example, they have very, very few shock hazards. So they're doing something right. We're not doing something right. So we need to have a paradigm shift. So there's got to be more risk analysis and more safety conscious efforts involved. Everyone wants to be a hero and go in and fix something right away without really thinking about what the hazard might be.
That's a good point. I know you talked a lot about standards in the presentation. Someone's asking, is it an NFPA or OSHA violation to check absence of voltage with a handheld proximity tester volt pin?
Oh, I'm sorry. Can you say that again, Alan?
Is it an OSHA or NFPA violation to check with a volt pin? We can get back to that one later. Let's see.
First of all, if it's low voltage, you should not use a proximity sensor because a proximity sensor will not test below a certain level. It's allowable in 1,000 volts or more because you're not really testing for the absence of voltage. You're testing for the absence of nominal voltage. And it's usually the utilities that get involved with using proximity sensors. So if you're testing a 5 kV system and you measure something other than 5 kV, you have other means of determining whether the voltage is present or not.
Okay, perfect. Someone wants to know, does this product come with dry contact to connect with PLC for remote monitoring?
We do have the first model of absence of voltage tester that does have a dry contact, which can change state when the green lights are on. And I think it's on the second one too, I believe. Yes. So yes, it does do that.
Okay.
The absence of voltage tester, not the VTI.
Okay. Can the ground fault protection panels be used with drives? And do the ground fault protection panels have the ability to withstand any DC offsets that may cause nuisance tripping?
I think the DC offsets are no problem because we're only measuring with the CT and we're not going to get the DC. The DC offset will not add to that. With drives, I haven't fully studied that yet. I think there might be some issues, but I'm not 100% sure because of the pulse wave modulation on the output. So I'll have to double check that. And that's a great question. I need to do a little bit more research on that.
Okay, perfect. Someone wants to know, how about installing IAVT on electrical panels in hazardous areas like Zone 0 and Zone 1?
We currently don't have a suitable enclosure for hazardous areas like that. But if there's a market for it, I'd happy to pursue that. How many does he want?
Let's see. What is the next one? What is the environmental rating of the IAVT and VTI?
The VTI, we're currently trying to get IP66, and with the IAVT, I think the same rating.
Okay. There's lots and lots of questions. Please continue to submit your questions. We'll get to those after the fact via email if we don't have time to get to all of them today, which obviously we're not going to be able to get to everything. Some really, really great questions. Let's see. Can the AVT be connected through a PT for high voltage gear?
No. But here's what. I'm currently working on a design that will try to put the AVT on the output of a resistor to monitor a 5 kV bus. So I haven't come up with the 5 kV source yet, but we've got the design, and as soon as we get that 5 kV source, we're going to try it out. The danger in putting anything in between the AVT and the source is the reliability of that device you put in the middle. So if you have a PT and you get a blown fuse, I don't want to leave you with a false sense of security. So if your fuse is gone, you have no verification that there's no voltage present on the bus. And this is the problem we have with putting anything in between the AVT and the source. But I am working on a 5 kV model. We already have the VTI up to 3,000 volts DC, right? Using the same type of technology, but the AVT, the complexity that I have with the AVT is I need to have very, very, very low impedance between the two pairs of wires. And that's my dilemma.
Okay. I think this is just a kind of a clarification. Someone's asking, is it correct to say that the VTI is to be used when the system is energized and the absence of voltage tester when the system is de-energized?
You can use, it depends what you want to use the tool for. If you want to verify the absence of voltage, then use the AVT. It's going to give you indication that the voltage is present, and it's going to give you a positive indication that the voltage is not present. If you want to measure the voltage on the bus when the device is on, use the portal, the VTI. If you want to do both, buy the combined unit.
Okay. I don't know if you already went over this. What is the highest voltage these testers go to?
The AVT and the AVT, I believe, goes to 690 volts, but it's 690 volts. But again, I said I'm working on a model that may go up to 4160 volts. The VTI goes up to 1,000 volts, and it's category 3 at 1,000 volts, and category 4 at 600 volts. And we have a model which we're working on, which is can go up to, theoretically, I can go up to 5,000 volts on that as well. But we also have a DC version that can go to 3,000 volts DC.
Okay, perfect. Here's a question from James. What is the voltage level of the supercapacitor?
My voltage level of this. 4.5 volts.
Okay. Someone wants to know, for specifying things, what should be the generic term for this equipment to be included in the spec to avoid proprietary issues if they're just writing out specs?
Well, I think the standard uses AVT, but you have 1436, and if they use AVT, I think you can use AVT, or just absence of voltage device.
Okay. We're getting close to time now. Let's see. Let's do one more, and then we'll definitely get to the rest after the fact. Is there any reason for 3 VDC? Why is it not 1 volt or 5 volt?
I don't know the reason why 3 volts AC or 3 volts DC, but the standard stated 3 volts AC or 3 volts DC. I'm not 100% sure why those were chosen, but if that's what we had to adhere to.
That's right. All right. Well, I think in the interest of making sure we respect everyone's time, we're a couple minutes over here. Great presentation today. We're out of time, though, for this webinar. For those questions, like I said, we didn't get to, we will definitely be getting back to you via email. And that concludes today's presentation. On behalf of EC&M, I'd like to thank I-Gard for sponsoring this event, and of course, to all of you for joining. Thank you and have a great rest of your day.